Welcome back, everyone. Uh, Welcome back from spring week and from your exam. Uh, Today, we're finally going to be starting some chemical reactions here, so stuff we've all been waiting for since the beginning of the class, right? Pretty much. Um, we're going to be studying these in detail. We're going to have probably about 3 weeks of chemical reactions, including math associated with them. That may touch in a little bit to acid base as well, but we'll see. We're almost done with the semester. We have just about a month left or so. So we've done it. We've gotten through most of it. So just a little bit to go, right? So this is going to be chapter 9, by the way, in our textbook. So here we go. So we're finally going to be talking about chemical changes. So remember that when we talk about chemical changes, we're involving changing composition of something. We've talked about physical changes almost kind of the entire semester. You know, we'd be taking a gas and moving it into a different container. That's a physical change because we're not changing the gas uh, and chemically in any way. It's still going to be, argon if we move it from one tank to another, or if we were to melt some ice, it's still water. We're not changing the composition of the substance. But now we're going to finally start doing that. So chemical reactions are going to be chemical changes. So we're going to go from some substance or substances to new different substances at the end of the reaction. And so those always kind of form the idea where we're going to have some reactant or reactants to a product or products. So we're going to see that all of our chemical reactions are going to kind of follow this sort of path here. And we're going to see that there's a lot of information that we can be given with a chemical equation, and we're going to have to work through all of it. So there's a lot for us to learn this chapter, so it'll be awesome. Alrighty, just one thing to note. We haven't talked about this in a while, but just remember that matter cannot be created or destroyed. Oops. Created or destroyed in a reaction. And we're going to see that that's going to come into play more when we talk about balancing equations. But for kind of how we're going to start, we're going to just look at predicting products of reactions first. And we're going to see for this class, we're really going to just be looking at 5 reactions overall, and that these are going to follow similar patterns that we're going to be able to predict what's going to happen over the course of the reaction. So let's just go ahead and hop into it. So let's talk about types of reactions here. So types of chemical reactions. We're going to see one first type is going to follow this kind of idea. We're going to have 2 things or more. We're going to stick them together and make a new thing. This type of reaction is called synthesis or combination. And so we're just taking 2 things and putting them together. For example, if we were to take hydrogen and oxygen, we could form water from those by burning them. Or if we wanted to, say, take sodium metal plus chlorine gas and make sodium chloride. That would be another example of a combination reaction or synthesis reaction. So we're just taking 2 things, globbing them together. Um, when you're asked to predict these reactions, when you are asked to predict the products of a combination, you will only be given ionic compounds. So for this class, when we're looking at combination reactions, I'm only going to give you things that are going to form ionic compounds, and ones that you'd presumably be able to figure out. So for example, if I were to give you, let's say, how about I give you, what would be a nice example here? How about I give you calcium plus fluorine. This one's an easy one. So if I were to give you this as a, and I told you it's a combination reaction, you would presumably be able to identify the product as calcium fluoride. Remember that calcium takes a charge of 2 plus, fluorine takes a charge of minus. So when we group those together, we need 2 fluorines in there to balance things out. Or if I were to give you, say, how about zinc and nitrogen? Notice we just have kind of two things we're putting together. That's how we can identify it as a combination reaction. For us, you would hopefully get this as your product. Remember, zinc is always 2 plus, nitrogen 3 minus. So zinc nitride will always have the formula Zn3 and 2. So it may also be a good idea to go back to remember your charge balancing. So hopefully that'll work there for you. All right. So any questions on combinations? These are pretty simple, not too crazy reactions. Alrighty. In that case, let's go ahead and look at our second reaction type, which is going to be the opposite. This is called a decomposition reaction, where we're going to take something and it's going to break down. Let's have some examples. Hydrogen peroxide will break down into oxygen and water. Let's see, calcium carbonate will turn into calcium oxide plus carbon dioxide. These are kind of just examples of decomposition. So we'll have some substance that's just breaking down. And as it does so, it's going to be producing multiple components. Nitric oxide breaking down. These are going to kind of be the only ones where you're going to see one reactant. That's going to be your hint it's a decomposition reactant. So, oops. That's how you'll know something is decomposition. And there's really only 2 decompositions I want you to be able to predict over this course. So 2 important decompositions. one of which is going to be carbonates. If you heat up a carbonate, it's going to break off a carbon dioxide and something else. So, for example, we just saw if we heat up calcium carbonate, we saw that it turns into calcium oxide plus carbon dioxide. We're going to see that the same thing will happen if we do that with other carbonates. What else shall we try? How about, I don't know, barium carbonate? Get the same thing. You get the oxide out plus carbon dioxide. So these will always produce the metal oxide and your carbon dioxide. So when you heat up a carbonate, oftentimes that heating is given just by a delta, by the way. That just means heat. So if you put a delta over your reaction arrow, it just means you need some heat to get it going. So these are heated up and they will give off carbon dioxide gas and leave the oxide behind. All right, the other decomposition we want to look at is certain oxides when heated as well. Will give off, will decompose in a similar manner. So for example, silver oxide, when you heat it up, can break down into silver and oxygen. Mercury 2 oxide can break down. These are even easier, right? You just kick off the oxygen and leave whatever's left. So that's the only other one I want you to be able to predict. So if you were to heat up an oxide, you'll probably end up kicking out the oxygen and recovering your metal here. These are typically pretty high heats that you need for some of these. So you get the metal plus oxygen gas when you heat up the oxide. All right, so this is again just for when I'm asking you to predict the products. If I'm just asking you to identify something as decomposition, any of these other ones could be, candidates. And you'll know that because there's only one reactant. So if you only see one reactant, it's a decomposition reaction. That's the only type that you're going to see just one reactant. So we're going to see for all of these, there's going to be kind of hints that'll tell you what type of reaction something is going to be. And then for decomposition, that's just, you're only seeing the C1. Yeah. So for predicting the products, that is. So you should still be able to, like, for example, identify the decomposition of hydrogen peroxide if I give you that whole equation as a decomposition. So if I say what type of reaction is this top one here, you should be able to tell me it's decomposition. But I wouldn't ask you to predict the products if I just say when hydrogen peroxide decomposes, what's the products? I won't ask you that. However, when I say when calcium carbonate decomposes, what are the products? That one you should be able to do. Or lithium carbonate, or whatever, some other carbonate you should be able to do. Okay, so hopefully that's not too crazy. So basically, you'll want to predict the products of the second one, but all three you should be able to identify as decomps. Okay. These first three reactions that we're going to be talking about are kind of the easier ones, and then we'll get into tougher ones here. Our third one is combustion. This is a very special type of reaction. Where we're going to take some hydrocarbon X and Y can be, any sort of combinations of things. Sometimes you'll also have oxygen in here too. But essentially we're putting those with oxygen, we're getting out CO2 and water. That's, kind of is how these are always going to look. So if we take propane and burn it, we get CO2 plus water. If we take benzene and burn it, we get CO2 and water. If we take glucose and burn it, we get CO2 and water. If I take, I don't know, C100 H2O2 plus oxygen, I get CO2 plus water. Perhaps there's a pattern here you're noticing. It can be any sort of combination of X and Y's. There are some restrictions, but we don't have to worry about those till you get to organic chemistry. But suffice it to say, you take a hydrocarbon, or something with oxygen, like carbohydrate perhaps, put it with oxygen, you get out CO2 and water. That's a combustion reaction. These are always your products. Of a combustion reaction. So if I give you any sort of hydrocarbon with oxygen, you better be able to spit out these two products. So easy one here, predicting the product wise. Hopefully not too crazy. And so we identify combustion by seeing it as some sort of hydrocarbon and oxygen gas. If you see those two as your reactants, it's a combustion reaction. And so remember, hydrocarbons are going to have hydrogen carbons. Sometimes they'll have oxygen, or sometimes you'll have other random elements, but as you can see here, it's mostly carbon and hydrogen. Sometimes you'll have other little bits, but you always produce CO2 and water when you do this. So the last of the easy ones for us. All right, any questions on these three so far? So again, the goals here for this kind of today's bit so far is you'll want to be able to, if given a reaction, identify its type, and if given a reaction, predict the products of it, if I give you just the reactants. And so that's the kind of harder part, but with these three, with combination, we're just looking at ionic compounds, so things forming their preferred charges. For decomposition, we're just looking at the carbonates and oxides. And then for combustion, it's always CO2 and water, so we don't even have to think about those. So hopefully so far these three are not too crazy. There will be plenty of practice for these, by the way. I have hundreds of problems for you guys to do. I found like little kind of like self-check quizzes you guys can use, so you can just generate problems, choose the type of reaction, predict its products, balance it. You can do all sorts of fun things with them, and it'll tell you if you're right or wrong, immediately as soon as you like click submit. It's not any points or anything. It's just a like kind of practice type of thing. So that's on Canvas. I'll probably make that visible to you guys later today. Alrighty. If there's nothing on those three, let's move on to the slightly more complex reactions. Reaction type number 4 is going to be single replacement or substitution. And how you'll identify these is this will always come in the form of an element by itself plus a compound and you're going to see that that will turn into an element plus a compound. For example, we have an element in the compound here, copper being an element by itself, silver nitrate being a compound. When we do this, we're going to end up kicking out our silver and substituting in our copper. Or let's say we have sodium bromide plus chlorine. Still, in this case, I've reversed it, compound and element. Remember, it's addition, you can just swap them, doesn't really matter. We're going to get out bromine. That's an element. And we get out a different compound at the end of the reaction. So we're going to see that when we're looking at this, that if your element that you're adding in, the element by itself, is a metal, that you're going to kick out the other metal. All right, and it's going to be the opposite for nonmetals. And so let's say we have this reaction here. We'll identify it as single replacement by noting that we have a compound and an element put together. So one of these reactants is an element by itself, the other one is a compound. We want to look at that kind of lone element. We'll say, okay, calcium is a metal, so it is going to replace the metal in the compound. The metal that's in the compound is magnesium, and so those two are just going to swap places. So as a result, we end up getting calcium sulfate plus magnesium. It just kicks it out. Right? So what's happening here is these two are switching positions. Our calcium is going to go and kick out the magnesium, and now the magnesium is out by itself. Or let's look at another one. How about we have zinc plus HCl. So HCl may not be so obvious for us, but we know that one of them is positive, right? The hydrogen should be positive in HCl. Remember, it's an acid. Acids have H+. if you want to think what is zinc going to replace, we remember zinc always forms a positive ion, right? So we're going to want to combine it with chlorine then. So we're going to end up getting, we're going to kick out our hydrogen and replace it with zinc. So just like before, we're going to kick these guys out. Just one thing to note, don't forget diatomic elements. So we can't just get H by itself. Remember, hydrogen always comes as H2, so that's something to not forget. I think we saw that in a previous example. Don't forget, we have all these guys up here. These elements are all going to be diatomic, right? So don't forget that those are diatomic. How about we do another one? What do we think is going to happen with this one? So what we want to do is look at our element by itself. The element by itself in this reaction is oxygen, right? That's the element. The compound is magnesium nitride. Oxygen is a nonmetal, which means we are going to replace the nonmetal in the compound. And so if we want to think about how that's going to work, if we want oxygen to come in and kick out nitrogen, we have to remember, okay, magnesium is always 2 plus, oxygen is always 2 minus. So if we want those to form a compound together, that's just MgO. The charges are the same, so they cancel out. And then we kick out our nitrogen here. So, another don't forget. Is that we can't forget our charge balancing. So notice we have to remember that zinc forms a 2 plus ion, chloride forms a minus 1 ion. So we can't forget that, right? When we kick these things out, we have to make the correct compounds. And if we're going to make the correct compounds, we have to remember our charge balancing. So again, it may be worth an hour or so or less, to review charge balancing. So if you want to remember that, that's somewhere in chapter 5, I think towards the beginning, if you've forgotten charge balancing. So it's super important, right? For the calcium and magnesium in this first example, it was okay because they both form +2 ions, so everything stayed the same. But just remember that magnesium and oxygen can only ever form one compound together. You cannot get Mg3O2. It does not work. That's not going to happen. So you always have to charge balance your products properly. All right, so let's do another one. How about we have, what would be a nice one? How about we have potassium plus if we take potassium and barium chloride, we have to look at our element. Our element by itself is potassium. Potassium is a metal. It's going to kick out the other metal, being barium. So we're going to need to now form a compound between potassium and chlorine. So we'll have to remember, okay, potassium always is +1. Chlorine is always -1. So the product, one of the products at least, will be potassium chloride, just KCl. And then you'll get your barium out. A very common thing that students make as a mistake here is they'll just say, oh, well, why don't we just get this? You know, I'm just replacing the potassium and the barium, right? That's a no-no, right? Because potassium and chlorine only ever form KCl. They don't form KCl2. They don't form K2Cl2. None of that. You always have to charge balance your products properly. All right, or else you're going to get some weird answer, some compounds that don't exist. So this is why these reactions are a little bit more complex, is because we have to remember the products are not so obvious to us. We have to charge balance them. All right, let's do another one. Shall we do? Yeah, let's do this one. This one's a little bit less obvious to us. I have a hint for us. Remember that water is, you could write it as H plus and OH minus put together. That's our hint for this. And so if sodium is going to come in, sodium is a metal. Metals form positive ions. It's going to kick out the H plus and put itself there instead, which will lead us to NaOH. We're going to kick out the H plus, leave us with the OH minus. And if we're kicking out the H plus, can we leave hydrogen like this ever? Remember, hydrogen is diatomic. We gotta have its 2 there. So all of these, always be on the lookout for 2 things: diatomic elements and charge balancing. Exactly. Yeah, so you should definitely get H2 there as your other product. All right, and let's just do one more. How about we do I don't know. I don't know that this reaction would happen, but whatever. We can pretend. Lithium iodide and sulfur. So look at your element. Your element is sulfur, the one by itself, that is. Sulfur is a nonmetal, so it is going to replace the nonmetal in our lithium iodide. The nonmetal there is going to be the iodine. So we have to remember, okay, what charge does sulfur make? Sulfur makes a 2- ion. Lithium is a 1+. So if we crisscross those, we get lithium sulfide, Li2S. And then when we kick out our iodine, again, that's a diatomic element, so we have to get I2 out of here. Right, so the products may not be super obvious to us right away. So charge balancing, diatomics. Let me just write that in purple. Very important is charge balancing and diatomic elements. So never forget these two things when you're kicking out things in substitution reactions. So you'll always identify a substitution reaction as an element in a compound as your reactants. And you're going to make a new element and a new compound as a result. All right, questions on that one? I know that one's a little bit more complex. Hopefully we have quite a few problems for you to see here. Again, you'll have plenty of opportunity to practice these. I'll put up that website so you guys can do your little quiz thingies. All right. Then the last one we have is called double displacement. And that is something called metathesis. But no one ever calls it that. Everybody calls it double displacement. How this is going to work is we're going to have two ionic compounds now. Two ionic compounds, and they are going to switch partners. We're going to end up with AY plus BX. They just swap partners. And so, visually you might say, okay, well, we have blue dot with purple dot. And then we have green dot with, how about dark blue dot? And over the course of the reaction, what's going to happen is you will just switch the pairs. So you'll have green dot with purple dot, and then the two blue dots together. Ta-da! Colorful and pretty. So they'll just swap partners. Alright, so how this might look in a reaction is you'll see that you have two ionic compounds being put together. That's how you're going to identify this as a double displacement reaction. And what you're going to do is you're going to swap the partners. So we look here, we see, okay, sodium was with chlorine. It's going to see the other partner, and you're going to form a new compound between those two. And that compound will end up being, well, let's just double check. We have sodium, which is a +1 ion. We have nitrate, which is a -1 ion. Putting those together, we get sodium nitrate. That's our first pair. And then we have our second pair, which is going to be the silver and the chlorine. And we remember, okay, silver is always a +1, chlorine is always a -1, so this reaction was nice to us. We could just swap things around and we get our product. So we just swapped the partners. So again, notice here positive things go with negative things and vice versa. We don't end up with silver sodiumide or something like that. Like, always make sure that you're putting a positive thing with a negative thing. So just swap either the negative parts or the positive parts. So don't end up like switching them off another way. So think of it kind of like foil or something maybe, where you have these kind of inside ones and the outside ones, right? That are going to be switching or combining to make new ones. We'll have plenty more examples of this as well. Let's do another one. Let's look at this one. We identify it as a double displacement reaction because there are two ionic compounds we're putting together. Two ionic compounds means double displacement. If it's double displacement, we're going to want to change our partners. And so we're going to make new compounds out of those and these. So I'm just going to be very consistent with how I'm doing this. Again, it doesn't matter if you put, like in the last example, if you put silver chloride plus sodium nitrate, that doesn't matter. You can swap them all you like. As long as the compounds are correct, it doesn't matter what order you put them in. So if we want, we can do the calcium one first in this one. Why not? Calcium, always 2+, is going to be forming a compound with sulfate. Putting those together, they're both the same charge. So we get calcium sulfate. And the other two, we're going to get potassium with bromine together. Potassium is always +1. Bromine is always -1. So we end up with KBr. All right. Any questions on those ones so far? Okay, cool. Let's have, I don't know. Let's go crazy with this one. Why not? All right. Ammonium carbonate and cobalt-3 acetate. A little bit more complex, just making things as more polyatomic ions. But look, still two ionic compounds. All we're going to do is swap the partners. So we're going to want to make a compound between ammonium and acetate. And thankfully for us, that's just all going to work out right here. They're the same charge, so we can just throw them together. Ammonium acetate there. And here's the tricky part. We know we're going to want to make a compound between those two. Well, we know carbonate is a 2 minus ion, but cobalt is variable charge, right? So what we have to do is look at the cobalt in the original molecule. If we remember, acetate has an overall charge of -1. If we have 3 of those, that means our cobalt is really cobalt 3 plus. So remember how to figure out the charge of a transition metal from a compound is you want to kind of reverse crisscross, or you can do the algebra stuff. So this cobalt is cobalt 3 plus, and that doesn't change over the reaction. We're going to see that the charge is still going to be the same. So it's cobalt 3 before, it's going to be cobalt 3 after. What we have to do is crisscross now, the cobalt and the carbonate. And we end up with cobalt 3 carbonate there. So thing to notice here is that charges don't change in the reaction. So cobalt was 3 plus beforehand, it stays 3 plus at the end. All right, so when we take it through, again, you may want to spend some time reviewing how to determine the charge of these. Go back to the Chapter 5 lectures on naming and charge balancing to make sure that that's going to be okay. So keep that in mind, okay? So don't forget about charge balancing there, or figuring out the charge of that. Notice, by the way, this is kind of a harder example. Let's go back to something a little bit easier. How about we do this one? What shall we make with this one? How about we take this and let's put it with lead I don't know, how about lead 2 nitrate? I guess I shouldn't have said the name, but I did. Oh well. So, as always, double displacement, we know that because we have 2 ionic compounds here. So we're going to make one between the iron and the nitrate. I guess I have to use green for this, so let me switch to green. Oh my gosh, go away. Alright, so we know we're going to make those there. We look at our original compounds. Hopefully we can tell that the iron here is +3, because chlorine is -1. There's 3 chlorines, so the iron must be +3. We know nitrate always takes a charge of -1. So one of the compounds that we're going to get out of here is iron 3 nitrate. And now let's look at the green one. Okay, so the lead here, the nitrate, remember, is -1. So having 2 nitrates is overall -2, which means our lead is +2. So that's lead 2. We know chlorine always takes -1. So putting those together, we get PbCl2 as our product. All right. One thing you've probably noticed is that these are different over the course of the reaction, and that's just fine. We don't have to worry about those yet. Always be afraid of the yet. But uh, this is okay. There's nothing wrong with this. We always have to charge balance. We do not say, we definitely do not say, okay, we can't just say, let's just swap them like this. No, 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 no. Always charge balance properly. All right, so we have to make sure that we look at the ions that these things are made up of. All right, so if you look at the ions things are made of, you'll always end up getting the right compounds at the end. We know also, if we were to name these, we have iron 3 chloride, and then we have lead 2 nitrate. At the end, we end up with lead 2 chloride, just switching them, and iron 3 nitrate. So all we're doing is the same thing with the names. We're just swapping the partners there. All right, and so if you can just, if you know the names, if you like this way, take the names, swap their partners, and then come up with the formulas from the names. That'll work too. So we do end up with lead 2 chloride, which is PbCl2, and we do end up with iron 3 nitrate, which is the FeNO33. So always charge balance. Don't look at the subscripts from the other ones. You only need those subscripts to figure out the charges. So don't get caught in the trap where you say, oh, well, it's a subscript of 3 here. I need a 3 at the other side. You do not. You might, but you do not need to. All right, let's do some, let me pop open our practice thing. So on Canvas, it's going to be here. Let me go ahead and let me pull it up so I can show you guys. All right, so let's see. Going to, oh, I guess this is already visible for you guys. But if we go down to, for example, this double displacement reactions practice, so just going to your home page on Canvas, you go down, I guess, quite a bit of ways. Maybe I'll move this up or something, but if we go to something like this, the double displacement reaction practice, you'll see you have a lot of double displacement reactions you're going to be able to predict. And the answers are going to be here at the end. The answer key is right here. There's some other stuff about solubility. That's something we're going to include a little bit later on. But if you want to just practice predicting the products, you can get those from this little worksheet thing here. And so notice that there's some that have the formulas, some that have the names. So that's one thing you've got there. There's also, if you just go to this balancing equations, even though we haven't talked about balancing equations yet, this is actually a website, so we'll just go to it. You can say, okay, I want 50 problems on identifying the type of reaction. And I want to say here, so let's look at these ones. What type of reaction is this first one going to be? Well, we have our 5 different types, right? And so we see here, okay, we have 2 things we're putting together to make a third thing, a new thing. Well, that's just a combination reaction, right? How about this next one? Well, we'll want to identify, okay, we have an element and a compound turning into a compound and an element. That tells us single replacement. And if we just skip to number 4 here, we see, okay, we have a compound and a compound turning into 2 new compounds. That's double displacement. Or we have one reactant. That tells us decomposition. And then look, here's a hydrocarbon being burned. Here's combustion. Let's just go ahead and see our answers. We see that we got correct the ones that we tried to do. And so, you can totally do as many of these as you want. So if you want 100 of them, go right ahead. Plenty of practice for this. All right, so thank this random Mr. Carmen from the interwebs. Very nice guy. So he's helping us out. And later, once we talk about balancing, you can use this to practice balancing equations as well. So you're going to end up with balancing up there. Did I not click both? Oh, I didn't click both. Whoops. Back we go. That's fine. So when we talk about that, we can also now do both balancing the equation and identifying the type. It's a very good resource for you to practice your skills. So this is a great website. Again, it's on Canvas. If we start at our homepage, that is just practice. You will have homework on this. Once I find it, I could make it visible to you guys. Look, here you go. Double displacement reactions. Have fun. That one you'll turn in. That one's just, it's a worksheet, just like always, that you'll turn in. If you want to start on that, go right ahead. But that other thing is just practice. So again, it's down here in the extra practice one. That's under balancing equations. So very useful little tool. If you just have 5 minutes here and there, just take a couple, do 5 problems, or something like that, and keep it fresh in your head, okay? Because this stuff, as you can imagine, will get pretty complicated. So the more you can kind of practice this stuff, the easier it's going to get for you. It's easier going to, you know what I'm trying to say. More practice equals good. So, good stuff. All right, so we're through for today. We will continue on this stuff tomorrow. I am going to be just moving forward, though. Like, for most of the problems, I'm going to just provide the products. But, as we do these, we're going to see we just keep adding on more and more stuff that it's going to be very build upon itself. So really, really try and practice this kind of step by step, because we're just going to keep adding more and more and more as we go through it. So, all right. I haven't looked at the exam scores yet, so I'll take a look at those. Someone wanted a box and whisker plot, so I'll try and, I haven't done one of those since stats class in like however many years ago, so we'll see if I remember how to even make one of those. But I'll take a look at that and we'll see how those are. So, alrighty. See you tomorrow.